Good morning, dear students. Today I am going to engage the class on additive manufacturing systems. So this will be the module 5 under the computer integrated manufacturing. With that, the unit number 1. Content of my presentation goes like Part 1, Additive Manufacturing Systems, Introduction to Additive Manufacturing, Difference between CNC and additive manufacturing, Functional principles, time compression in engineering, additive manufacturing process chain, additive manufacturing applications and uses. And the later in this part 2, I'll be taking up the additive manufacturing processes in detail in my next class. Introduction to additive manufacturing. The term rapid prototyping or RP is used to describe a process for rapidly creating a system or part representation before final release or commercialization. A recently formed technical committee with the ASTM International has agreed that new terminology should be adopted. Recently adopted ASTM consensus standards now use the term additive manufacturing. The basic principle of this technology is that a model is initially generated using a computer aided design, that is a CAD design, and can be fabricated directly without the need of process planning. This is with the beauty of the process. Without any kind of process planning, a part is directly going to be obtained. The roots of the rapid prototyping or additive manufacturing can be traced to two technical areas. That is, first one is the topography, and second one is the photosculpture. Topography is a layered method was proposed by Blanter as early as 1890 for making molds for topographical relief maps. Both positive and negative 3D surfaces were to be assembled to form a series of wax plates cut along with the topographical counterlines. This method was further refined by Pereira and the Mutsubara, who describes a layer manufacturing process to form the casting molds. The layers of molds are produced from the refractory particles coated with the photopolymer resin. The resin is selectively cured using sunlight. Similarly, many of the authors have proposed a process for layer manufacturing 3D objects from contoured metallic sheets that are formed using a milling cutter. Nakagawa reports the use of laminated techniques for fabrication of blanking tools, press forming tools, and injection molding tools. The second one is the photosculpture. This is a technique proposed in the early 19th century for creating replicas of 3D objects. The technique involves the photographing the object simultaneously with the 24 cameras equally spaced around a circular room and then using the silhouette of each photograph to carve 1/24th of a cylindrical portion of the object. Attempts were made by another developers to improve the technique by elevating the manual carving steps. Many of the pioneers proposed the use of structured lighting to create a contour lines of an object photographically, then using these lines to cut and build the object from sheets. In 1956, Munz patented a layer manufacturing system for fabricating the cross sections of a scanned object by selectively exposing transparent photoemulsion. The system produces layers by lowering the position in a cylinder and adding appropriate amounts of photoemulsion and fixing agent. The need for the prototypes. After having studied about the need for the rapid production or rapid manufacturing or rapid prototypes, we have to understand what is the basic idea behind the prototype fundamentals. The general definition of the prototype contains three aspects of interest. First one is implementation of prototype. So this can vary from entire product itself to its sub-assemblies and components. For second one is the form of the prototype. For from a virtual prototype to a physical prototype. There may be classification of the prototypes, which are virtual prototypes in the sense they've been using only for the reference, for the study, and then towards the physical prototypes, which are very similar of the actual product but may be different with the material. Degree, third one is the degree of approximation of the prototypes. From a very high rough representation to an exact replication of the product. Generally, we do the prototypes for initialization of production or a product. During the preamble to any kind of new product development, these prototypes play a very vital role in understanding the product and its forms. Introduction to additive manufacturing or layer manufacturing. In this session, we are going to use repeatedly the terms additive, layer, rapid, digital, etc., where additive reflects the additive manufacturing, abbreviated shortly as AM, additive layer manufacturing as ALM, additive digital manufacturing DM. With respect to the layer, we have layer based manufacturing, layer oriented manufacturing, layer manufacturing. Adding the term rapid, we can make the technology rapid prototyping, rapid tooling, and rapid manufacturing. Digital fabrication and digital mockups are very essential in order to use the additive manufacturing technology into any kind of production. Advancedly, we have 3D printing and 3D modeling, and we also have direct manufacturing and direct tooling, which are the recent outcomes of this additive manufacturing. Let us put an highlight into how the additive manufacturing has been evolved. The understanding of this evolution goes way back into 1770, where the early mechanization of the manufacturing activity was seen. In 1946, the very first commercial computer was invented. 1952, the first numerical machine tool got into the production shop. 1960, the first commercial laser, which was invented into production activity. 1961, first commercial robot. 1963, first interactive graphics system. Early version of a computer-aided design was seen in 1963, and in 1988, first commercial rapid prototype system was evolved. Additive manufacturing evolution. As I said earlier, Munz and Blanter, it is two people who have been used this concept of additive manufacturing, and they used it for the topography and photo sculpture. A Munz has developed a model which works in the area of the rapid prototyping and was continued to work till 1970, and he has got more number of patents on this area. This is a method he uses fabricating objects from powder materials by heat particles, locally and fusing them together, employing a laser, electron beam, or a plasma beam. This is the process for producing plastic patterns by selective 3D polymerization of a photosensitive polymer at the intersection of two laser beams. Mun's model is also having used with a photopolymer for building objects in layers. A mask is used to control the exposure of the ultraviolet source when producing cross-sectional model. And the Blanker, who has used it for the photo sculpture, creating a layers. This is what you could see. If the figure number 2, there are tiny layers which have been added. Either it can be over a positive side or over a negative side. Dear students, let us find the difference between additive manufacturing and CNC technology. And due course of your studies, we've been admitting the facts that the additive manufacturing is a newer technology. Nevertheless, CNC is also a new technology for manufacturing. Let us have a compilation between the additive manufacturing and the CNC technology. The A, figure A represents the CNC technology wherein the subtractive manufacturing is going to happen. You see in the figure, a raw material is taken and it is processed under a machine following the subtractive manufacturing. Then what happens? We are going to get a 3D object wherein you could see the material is removed from this block, and finally we are going to have certain waste which is come out of the raw material, and finally we get the part. Similar process is applied on the additive manufacturing, but here what we use is the reverse of the process, and the material is taken in the form of a powder, liquid, or any other form, and that is subjected to additive manufacturing, wherein, as the name itself indicates, adding things on taking place. It adds things, it adds materials. As it adds the materials, we can bring up a 3D object by having a layered manufacturing techniques, and finally results with the unlimited waste. This is how we are going to use additive manufacturing effectively with having a least waste at the end of the process. The functional principle which is involved in any additive manufacturing method involves material development, design modeling and simulation, materials processing and layering, final product. In front of me I have a model of cup. Initially the designers are going to create a 3D model of it. Once the 3D model is created, they are going to get its STL file. STL file is specifically a file that is related to additive manufacturing process. I'll go in detail of this STL in my next sessions. And after this STL slides are formed, files are formed, we have the sliced layers and generating the toolpaths. Once this is done, we are going to introduce that into the 3D printer, where 3D printer builds the model geometry by adding layered material. Finally, at the end, I have the 3D object. The system starts by applying a thin layer of the powder material to the building platform. Powerful laser beam which fuses the material exactly at the points defined by the computer generated contours. Platform is then lowered to make a fresh layer of powder exposed onto the laser. Once the material is fused so as to bond with a layer below that the predetermined points, this process kept on repeating. So need for additive manufacturing. Why exactly we wanted this additive manufacturing to be implemented? Well, think of this particular condition. We come across a term called time compression engineering. Time compression engineering is also known as concurrent engineering. The main enabling technology behind time compression engineering is 3D CAD modeling. Concurrency means performing different design and manufacturing activities presents an opportunity to compare the overall product development time, whilst opening up possibilities to be created by providing more time for design interactions. We have narrated this with the aid of a diagram in front of you. The serial method of producing a part follows with a conceptual design, detailed design, engineering analysis, prototyping, tooling, and production. So this is what we see. There is a sequential process taking up. Conceptual design, detailed design. Again, once the conceptual design is completed, a detailed design will initiate, and so forth. If suppose anywhere any process got stumbled or delayed, so that makes the entire series of this particular activity on hold or maybe delayed. So that makes the entire product development process to be on slower pace. Rather, thinking of about the concurrent engineering, I can make the body of the concurrent manufacturing or concurrent engineering clubbed or divided into conceptual design phase, virtual prototyping and engineering analysis, and rapid prototyping and manufacturing. So when I think about the 3D CAD modeling, this encapsulates the conceptual design and the detailed design. So this is how the two sequences club together to make one as 3D CAD modeling, and which are interconnected to each other. The next phase will be VR and FEA, virtual reality and finite element analysis. So this will take care of the virtual prototyping and engineering analysis, where the virtual prototyping means the creation of a product at the virtual area, the virtual field, and the engineering analysis does the optimization part on the product with the design features. Followed by rapid prototyping and manufacturing. This is where the manufacturing is going to take place. So this again divides into three stages, that is prototyping, tooling, and production. Any production activity that must be supported with the tooling. Making of a tool itself costs us the long duration. But when think of additive manufacturing in terms of time compression engineering, directly we are going to get a tool which is manufactured relating to the part while preparing with its prototyping. Therefore, the production will be made much easier. When we compare the serial as well as the concurrent engineering process for manufacturing, we can find time savings which will be around 20 to 22% of time that is saved when we use the concurrent kind of manufacturing technique. So this is how the advancement in computing technologies, computing facilities that enable us to go for shrinking in the production time for the components. Generic additive manufacturing process. So there are 8 stages of generic additive manufacturing process, and these 8 can be explained as conceptualization and CAD, conversion to STL, transfer and manipulation of STL file on additive manufacturing machine, machine setup, building, part removal and a cleanup process, post processing of the part and the application. Let me come to explain one by one. Step 1, the conceptualization on CAD. Conceptualization is nothing but the concept creation by the designer. Any creation is again the capacity of the imagination. Engineers, the designers who can think innovatively, and it is their capacity to devise a newer component having an attractive features in it. Conceptualization in CAD, that makes easy with the aid of a CAD because computers are the part. The generic additive manufacturing process starts with the 3D CAD information. There may be many ways of how the 3D source of data can be created. Obvious. The model description could be generated by a computer. Most 3D CAD systems are solid modeling systems with some surface modeling components. Step 2, conversion to STL. The term STL was derived from stereolithography, where I'm going to explain this stereolithography in my next session. STL is a simple way of describing a CAD model in terms of its geometry. It works by removing any construction data, modeling history, etc., approximating surface of the model with a series of triangular facets. STL is also abbreviated for is the structural triangulation language or standard triangulation language. And this has the ability of minimizing the size of these triangles, which can set with most of the CAD softwares. And the software is having an objective to ensure the models created do not show any obvious triangle on the surface. Continuing with the process 2 here, the process of converting STL is automatic with most of packages. Recent CAD packages have this ability wherein they can convert any 3D model into STL file format. And these are the file formats which are readily accepted by the additive manufacturing machines, and thereby it starts producing. It is just like having an example here. You have a document typed in a computer using appropriate softwares. But when you wanted to take the hard copy of this soft version of your type, you need a printer. Printer here assumed to be additive manufacturing machine. But in order to interface your computer with the printer, we want a printing software. So this printing software, what enables our computer to get the soft form of the document into the hard form of the document. So we require the program. So this program is STL in terms of additive manufacturing. With complex geometries, it may be difficult to detect such problems while inspecting the CAD or subsequently generated data. Because when we have manufacturing as a process, the part geometry is unlimited. Some geometries may be simpler, some geometries may be very complicated, and having this complicated geometry sometimes goes on giving errata on STL file formats. If the errors are small, then they may even go unnoticed until after the part has been built, and this will be referred during its quality inspection. STL is essentially a surface description model. The corresponding triangles in the files must be pointing in the correct direction. Either it can take clockwise direction, counterclockwise direction, upward, downward, any of the direction. While most errors can be detected and rectified automatically, there may also be a requirement of a manual intervention. Most of the times, human intervention is very essential to verify the component geometry. Step 2. Continued. Here, standard triangulation language, or it can also be said as a stereolithography. STL file format is given in the diagram. You can find here a cylindrical part that has gone converted into STL file format. You could find the inside circle and outside circle, right, in red color. And when you focus very close onto the diagram, we will find this circular geometry has gone converted into many form of triangles. And you can find there are three lines here, A, B, C, moving in a clockwise. You can find three triangles, right? And each triangle having three sides. So three triangles, obviously you think about nine sides. But here what happens here, you see A has 1, 2, 3, and B has 1, 2, 3, and wherein the side C as the side A sharing between the triangle A and C, and the triangle B is going to share that edge between triangle B and triangle C. Therefore, we have shared the edges of these triangles. By doing so, we can have minimum memory for storage of the geometry. conceptualization and CAD, conversion to STL, transfer and manipulation of STL file on additive manufacturing machine, machine setup, building, part removal and a cleanup process, post processing of the part and application. Step number 4, machine setup. All additive manufacturing machines will have at least some setup parameters. That is obvious. Some machines are only designed to run perhaps one or two different materials, but some machines are having given with this capacity to have the variation in the layer thickness or build geometries. In the more complex cases, to have default settings or save files from the previously defined setups help speed up the machine to set a process into prevent mistakes, because sometimes the previous machine data will be taken to process the present running. Normally, an incorrect setup procedure will start result in a part being built. Moving on to the step number 5 is build setup. The first few stages of additive manufacturing process are semi-automated. That means it may take a required considerable manual control into account, where the machine is interacting with the human for decision making. Once these steps are completed, the process switches on to the computer controlled building phase. It's nothing but automatic phase. All the additive manufacturing machines will have a similar consequence of layer control using a height adjustable platform, material deposition, and the layer cross section formation. All machines will repeat the process until either the build is complete or there is a no source material is remaining. That means this is the part. The functional principle which is involved in any additive manufacturing method involves material development, design modeling and simulation, materials processing and layering, final product. In front of me I have a model of cup. Initially the designers are going to create a 3D model of it. Once the 3D model is created, they are going to get its STL file. STL file is specifically a file that is related to additive manufacturing process. I'll go in detail of this STL in my next sessions. And after this STL slides are formed, files are formed, we have the sliced layers and generating the toolpaths. Once this is done, we are going. Step number 7 is the post processing. Post processing refers to usually the stage of finishing the parts for application purpose. This may involve abrasive finishing like polishing, sandpapering, or application of coatings. And this post process sometimes also involve for reheating of the part just to enhance the curing or achieve the proper curing. Step number 8 is application. The intention of having any additive manufacturing part is to have application. Following post processing, the parts are ready for now use. Although parts may be made from similar materials to those available from the manufacturing process like molding and casting, parts may not behave according to the standard material specification. Some additive manufacturing process create parts with small voids, bubbles trapped inside them, which could be the source of the part failure or mechanical stress. Some process may cause the material degrade during the build or material not to bond, link or crystallize in optimum way. This is how the design part when applied with the application will not behave as planned. So moving on to the applications. Additive manufacturing products are applied everywhere. They can be used as functional models, pattern for investment and vacuum casting models, medical models, art models, engineering analysis models, rapid tooling, new materials development, bimetallic parts means having two materials, remanufacturing, applications, examples for aerospace, defense, automobile, biomedical, and general engineering industries. The use of additive manufacturing to support medical application. One of the important application of additive manufacturing finds in medical applications, surgical and diagnostic aids of the human models. See, there are so many complex operations to be conducted on human beings during their injury. So directly having done operation and experiencing the trial and error things on a patient, it is better to have the surgical procedure conducted on the additive manufactured models of the same human being. Therefore, the surgery can be studied. And another important application is the medical application is prosthetics development. Any breakage in the human body parts that can be developed and can be replaced. Manufacturing of medically related products like hearing aids, which are very complex in design and very small in shape, it is very difficult to have the machines deployed to make them. And also, the other thing is that a very recent and the latest application seems to be tissue engineering. The ultimate in fabrication of medical implants would be the direct fabrication of the replacement of body parts. Like we can make the replaced body or any part that is worn out can be replaced, like the ball socket joints, the hip sockets, or any chip, right? Any other parts, small tiny bones of any finger, the the broken part of a skull, which can be replaced by using additive manufacturing. Step 2, conversion to STL. The term STL was derived from stereolithography, where I'm going to explain this stereolithography in my next session. STL is a simple way of describing a CAD model in terms of its geometry. It works by removing any construction data, modeling history, etc., approximating surface of the model with a series of triangular facets. STL is also abbreviated for is the structural triangulation language or standard triangulation language. And this has the ability of minimizing the size of these triangles, which can set with most of the CAD softwares. And the software is having an objective to ensure the models create. Further, moving on to applications, you can find applications like the perfume bottles with the different capacity, different forms, different shapes, cast metal parts, RP metal, sand casting, investment casting models, the impellers of pumps using the RP patterns. We have the facial part of that, the patient, then the polycarbonate investment casting patterns, and the housing of a component, and some kind of other ornamental devices, ornamental parts which are found profound with the additive manufacturing. Dear students, let us find the difference between additive manufacturing and CNC technology. And due course of your studies, we've been admitting the facts that the additive manufacturing is a newer technology. Nevertheless, CNC is also a new technology for manufacturing. Let us have a compilation between the additive manufacturing and the CNC technology. The A, figure A represents the CNC technology, wherein the subtractive manufacturing. Additive manufacturing and the subtractive manufacturing. The earlier I gave a glimpse here when I discussed about the additive manufacturing. Let us see a component here, the spherical ball, which need to be produced. I have two methodology here. The first methodology is subtractive manufacturing, other one is the additive manufacturing. The first diagram given here, that is, a spherical ball is obtained by removing the material, by machining process. And the second one is the additive manufacturing process. So this will tell us about the layered approach. The material is going to add on the layers, and these layers are clubbed together to form the component. So here the five parameters have to be required to study here. First one is the part complexity, material to be used, the speed of the process, number of parts or quantity, and what could be the cost of the production. If you compare all these five parameters over additive manufacturing and subtractive manufacturing, additive manufacturing reveals to be the best select candidate for kind of manufacturing. Now let us put some highlight on how CAD model get into the STL format. It is standard triangulation language, structural triangulation language, or it is a stereolithography. I have said that the STL file format is nothing but given the geometry of the part, the software is going to make the geometry into number of triangles, and these number of triangles get stored with their vertices or the corners or the edges, the data as x1 y1, x2 y2, x3 y3, etc. STL uses triangles to describe the surface to be built. Each triangle is described as 3 points and a facet normal vector indicating the outward side of the triangle in a manner similar to the following. It is the file format. The facet normal 4.47029 E02 7.00. This is how the value is given for x and y. Outer loop, inner loop, and with this kind of data format, every triangle data is stored. In my next class, I'll be discussing about the detailed classification of additive manufacturing and the additive manufacturing techniques. Thank you for the patience hearing. Thank you all. Thank you.